Hey everybody! The purpose of this video is to walk you through question E10 from the variation homework. This is a piggyback question. It's tied back to question, I think, E2 from the center homework. Back in that homework, you had a data set that had a certain average. And we showed back then that if you decrease all the data points by a value of 5, the average is also decreased by 5. So you might want to watch that video that goes along with that one to kind of refresh your memory about that one. If you're okay with that, if you're cool with that, then we'll move on to this one, which assumes that we believe that the average is decreased by 5, but that the standard deviation doesn't change at all. And I do have a corresponding video using Excel to explain this one. But what this one's going to do here is to prove it for you, kind of like E9 did in this homework, for any data set whatsoever, that the standard deviation is complete. Pardon the phone. The standard deviation is completely unchanged if the shift is a linear transform, decreased by a certain amount or increased by a certain amount. So what's cool about this one is it seems so counterintuitive. Like in the previous one, in E9, when we doubled the data, we doubled the standard deviation. And you can kind of apply that logic and say if you cut the standard deviation, you cut the data points in half, you'll also have the standard deviation. Now we're talking about just increasing by a fixed amount, not doubling, not multiplying, but just adding or subtracting, however you want to look at this. Why would the standard deviation remain completely unchanged? Well, that's what I want to kind of look at today. I want to kind of look at that. So here's the original standard deviation. I want to show that the standard deviation of our down by 5 data is going to be equal to the exact same thing. And we're going to kind of do it algebraically. Now, in order to do it algebraically, I have to apply this definition to that new data. So, we're going to start with a big old square root, which is what encompasses all of this. And we're going to remember what this sum means, and that sum is kind of not in the right place. It should be up there. Okay? The sum of the squared deviations. The first one is going to be the first x value. Now remember, the x values we're talking about, x sub 1, are decreased by 5. They're decreased by 5. Okay? We're going to subtract from that the new average, which is x bar minus 5. Now, that looks like a lot. And it is kind of a lot. But it'll collapse itself nicely. We also have to do that with every single other data value. Now I have to apologize, the board I have to write on is not all that big. So we're going to just say dot 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 for all the other data points all the way down to the last one, which is x to the n minus 5 minus x bar minus 5. All squared and all over n minus 1. Now this looks absolutely god-awful, but check this out, it's not so bad. Once you apply some really simple arithmetic in here, let's distribute this negative sign. This whole first piece is x sub 1 minus 5 minus x bar plus 5, the quantity squared. If we had room on the board, the next one would be x sub 2 minus 5 minus x bar plus 5. X sub 3 minus 5 plus minus x bar plus 5, and so forth and so on, all the way down for all the points to x sub n minus 5 minus x bar plus 5, the whole quantity squared. And we're still averaging that. Well, now we get happy, because there's a subtracted 5 and an added 5 term that cancel. A subtracted 5 and an added 5 term that cancel. And in every single one of those quadnomials, I don't know what you would call that, a quadnomial squared, you're going to have a negative 5 and a positive 5 canceling each other. And at the end of the day, what that means is you're going to have x sub 1 minus x bar squared plus x sub 2 minus x bar squared plus x sub 3 minus x bar squared plus x sub n minus x bar squared all over n minus 1. And then you get a little bit happy because you realize what this is, what you're looking at down here, is simply just the sample standard deviation that you had up here originally. Notice how the 5s are gone. Every phase shift of 5 has completely undone itself, because the phase shift of 5 from each data point is undone by the fact that the average was also phase shifted by 5. I said that in the original video. If you watch the Excel explanation, I mentioned that the averages are all shifted, as are each data point. Well, you can see that right here, and right here, and right here, and right here. And for every other data point involved, you're going to have the exact same shift. So there's absolutely no difference in the average distances from each of the data points to that average. They're all exactly the same. And that's the beauty of it. That's the beauty of it. This reduces right back to the original. There's absolutely no difference in the standard deviation if you apply a linear transform to it. That's actually a pretty important principle for those of you that go on to higher statistics classes. They use those linear transforms a lot, and the conservation of variation, I believe is what it's called. But it's a slick result, and it's kind of counterintuitive because we spend so much time in the previous lessons. When you decrease a data set by 5, you decrease the average by 5. You decrease the median by 5. When you double a data set, you double the average, and you double the median. When you double a data set, you also double the standard deviation. And then all of a sudden, this guy comes at you. This guy comes at you. When you decrease the data set by 5, the standard deviation stays exactly the same. And that's pretty slick. That's pretty slick. So I hope this made sense. I hope it didn't cause too much vomiting. And if you don't like algebra, like I said, you can always turn it off.